Okay, good afternoon, students. I'm just looking at around faces. It's nice to stop and, it's nice being a teacher. It's nice teaching you guys. Most of the time. Sometimes just looking at your guys' faces is enough to cheer me up. All right. While you guys are getting your chairs squared away and so forth, let's just take a look at this outline for today. First thing we're gonna do is look at the schedule of the next 2 weeks, just so everybody's clear about it. And then we're gonna continue our discussion of this mysterious energy concept, specifically more about potential energy. And then we're gonna work out kinetic energy and gravitational potential energy for the space shuttle as it transitions from orbit to the landing strip at Kennedy Space Center. And it's a huge amount of energy. And I think it's instructive. And then in part 4, we'll start talking about the rest of, no, I think it's chapter 5, angular momentum. So we'll do that. And then there'll be some homework this weekend. And I looked at some of the stats for homework 5. Raise your hand if you felt you did better on the brain burner on homework 5 than last time. Okay, I see a few hands. Good. And what we're going to do, we're going to keep working on that from time to time as we go through the next few weeks. Here's our SI schedule. Did you have any buddy today? Good. All right. And we're just going to keep working it together, 50-50. I'll be teaching and you guys will be learning. And you guys are learning, I know some of you feel a little nervous. I look around here and I know that there are some of you that have posted stuff about, I'm not very good. I'm not getting it. But you stick with me and you'll be surprised by the end of the semester. Now, forget about the end of the semester for the moment. Let's talk about the next 2 weeks. Okay, here's our basic calendar for the next few weeks. Here's where we are today, lecture 14. And so we have 2 lectures next week, and then the Tuesday after that, on the 3rd of March. Is that what this is that what the syllabus says? March 3rd? Who's got a syllabus handy? Is that March 3rd? Okay, good. Okay, so exam 2 on March 3rd, and guess what we're going to have a lot of? Or guess what we're going to definitely have as a prominent part? Stopping time, stopping distance. Okay? And we'll have plenty of practice before that. In fact, and then lecture 18 comes after exam 2. And then after that, spring break, which is definitely not coming a day too early. I wish we could have had it earlier. At least one spring break. And one more thing. You guys are really doing good, and we're actually ahead of the schedule for lecture. So that means I can give extra homework if you want, and I know that, definitely. We got people around. I see a guy in the back row going, yeah, flexing his muscles like he's Arnold or something like that. But on that weekend before exam 2, yes, we are going to have a special kind of a review homework. We might have a regular homework and then a second kind of a review homework. And guess what? It's going to involve Michael Jordan and Space Jam. So, and I've got all that worked out and stuff. It's pretty nice. So that's kind of where we're going in the next couple weeks, and hopefully we'll cover a lot of material, and you guys will be blazing intellects of science in the next 2 weeks. But let's pause for questions. Chanel. Spring break starts on the 9th, correct. That's the first official Monday of spring break. It's on the, if you don't know it already, if you're a newbie here at UCF, you go to the registrar's webpage and look at the academic calendar, and it'll tell you the days, like if we have President's Day off or something, or Columbus Day, and it'll also have spring break and various other days. Down towards the bottom of the academic calendar, it lists that. Another question. Okay, let's keep going. Potential energy. We want to continue talking about this. And for us, potential energy is associated with one of the four physical interaction forces of the universe: gravitational, electromagnetic, and then there's two nuclear forces. Now, we're not going to dip into that stuff because you need quantum mechanics. But electromagnetic, yes. And gravitational, that's what we're working on now. So let's take a little bit of look at the generic formula for gravitational potential energy. Now, this is at the surface of the Earth, where we replace the full G m1 m2 over r squared. That's always true. But on the surface of the Earth, you can replace it by mg, because you're not, the distance from the bottom of the Mariana Trench to the top of Mount Everest and everywhere in between, the acceleration is pretty much 9.8 everywhere. So this is a good formula for this. Now, if you were doing gravitational potential energy way out towards the moon or something like that, yeah, then you'd have to use a lot of calculus too. But for us guys, this is going to be sufficient. Now, what this means is that it increases when delta y is positive. Now, look at that expression. There's a minus sign out in front to indicate opposite of the work done, because the work done is mg delta y. All right, and the minus sign means take the potential energy is the opposite of the work done. Whatever work is done, potential energy is the opposite. So that's that first minus sign. And then inside the G is another minus sign, because remember, G equals negative 9.8 meters per second squared for downward direction of the acceleration due to gravity. All right. So if delta y is a positive number, look at you've got a negative times the positive mass times a negative 9.8 meters per second squared times a positive delta y. So if you're going upward, your change in your y position is positive. You're going like from down here, y equals 1 meter above the floor, to up here, y equals 1.5 meters. So delta y is 0.5 meters positive. All right, so when you go up, GPE increases. That means you lose kinetic energy and you increase the potential energy, right? By the same token, the GPE decreases when delta y is negative. So look at it again. Look at that expression again. You have the minus out in front, and then you have a negative sign inside of G. And then if your delta y is also negative, so that's like going from 7 meters down to 1 meter. That's a delta y that's negative. You drop 6 meters. Okay. You lose potential energy. You've got 3 negative signs in that. So negative times negative is positive, times another negative, total is negative. All right. So that means that when you lose elevation, you're dipping in the gravitational potential energy value. Right? You're losing potential energy to kinetic energy. And that's what happens. When you go downward in the gravitational field of Earth, you pick up more speed. All right? And so you lose potential. Now, the potential energy is a very, very special function, a very, very special concept. And it wasn't until about the 1800s or so, so that'd be about 200 years ago, that we figured out, yeah, this whole idea of energy of position is pretty important. For every kilogram of mass and for every meter of altitude, all right, above your baseline, whatever that happens to be, the GPE is defined, some number of joules, all right? Now, if you have a different mass, if you start out calculating with a 2.6 kilogram frozen chicken and you switch to the space shuttle, you got to, calculate because you got a lot more mass. And but other than that, yeah, GPE is defined everywhere. Everywhere in the gravitational field. Now, this is near the surface of the Earth. So this is everywhere from the top of Mount Everest all the way down to the Marianas Trench. And if you think of the sea level as your y equals 0, then Mount Everest would be about, 29,000 feet. Y equals 29,000 and change, something like that. I mean, it's up there. It's almost 6 miles to the top of Mount Everest. Anybody here ever been to the top of Mount Everest? No? Yeah, I didn't think so. It's pretty rare, people that have been up to the top, even though a lot of people have been up there. So as a result of this, you can define it everywhere in the gravitational field of Earth. And if you go a little further out, it's a little different formula, but you can still do the same thing. And so that's why we call potential energy the energy of position, compared to kinetic energy, which is the energy of motion. 1/2 mv squared. If you don't have any motion, you don't have any v squared, you don't have any kinetic energy either. But you might have potential energy, and in that case, you can get some kinetic energy from that, trading altitude for speed. All right? So this whole idea that potential energy is a function of position is a powerful thing. And one of the reasons is that energy as a function of position, the mathematics for it is easy. You don't have to do any trig or right triangles or anything like that. You just have to calculate, mg delta y minus mg delta y, and ding, you're good. You just got to know how far up or how far down something is moving. But but for forces now, you can have a force and an acceleration. Those are vectors, and you got to do a little bit of trig. I mean, if you're going to do them completely. Now, we kind of bypass trig for the most part. But think about, in the textbook, there's some examples of forces in 2 dimensions, and they're, you use Pythagorean theorem and stuff, and maybe some trig and figure this and that out. But energy is much easier to work with. So, and that's why I always say that the work formula, if you're trying to do a stopping distance problem, the work formula is usually the easiest one to start with. Delta KE equals F delta X, whatever your force is. Or it might be F delta Y if you're going up and down on the Y. Or F delta R if you're going radially outward from the center of the Earth or from the center of the sun or the center of some asteroid out in space. It doesn't matter. All right, so the energy of position is pretty important for us. And I've kind of alluded to that because in Einstein's 4-dimensional theory of space-time, we have these spatial dimensions and then the time dimension, that's the 4th dimension. And then dynamically speaking, we have momentum vector, and then the energy is the 4th component. It's what we call a 4 momentum. The energy is actually the 4th part of that. And so it all kind of corresponds very nicely. Now, let's talk about the space shuttle reentry. Now, what you're looking at here is an infrared image and then converted into false color. So the different yellows and reds and stuff. Normally, if you're looking at an infrared detector, you'll just see grays. Or maybe if you're in the Army, you'll see greens and stuff like that, right? For the night, if you have night vision goggles. But this is a false color image. It's taken from an Air Force plane, and the space shuttle, it's on reentry. Now let's look at some of these specs over here. This is March of 2009, STS-119. So it's coming in. They can measure the speed. They track it. They can figure out the speed, distance and time. They get that. Mach 9.1. Now that is faster than any known jet that we or the Russians have. I mean, we've got some pretty fast jets, but not that fast. And this is not a jet. It's coming in, from orbit. It's coming downhill from its orbit about 200 miles up. And at the point that this was taken, 160,000 feet, that's about 50 miles. All right. So, sorry, 50 kilometers. All right. So that's, they say that 100 kilometers is about the edge of space, the official edge of space. So this is halfway down from space. All right. And the distance from the aircraft to there, it says 28.2 nautical miles. So what that means is that the space shuttle's up here, and the space shuttle's about 50 kilometers up, and the aircraft is down a little closer to sea level. It's about 28.2 nautical miles. So, and it's probably off a little bit at a slant. It's probably not right underneath the space shuttle. But they do this all the time. They track, the NASA tracks, and the Air Force track the space shuttle location from airborne observatories. And we also keep an eye on what the Russians have got up there. You could do the same thing with them. It's a little harder because they're higher up. But on the day side of the Earth, they'll be hot from the sunlight burning down onto them from space. No clouds, no atmosphere, just nice, a lot of solar heat. So every Russian satellite will get hot, and you can see it on infrared if you know where you're looking. We got radar and stuff too. So, all right. So this is kind of where we're starting with. So what we're going to do, if you think about this, we've got some altitude, 50 kilometers. So that means we've got some GPE. All right. So make a note of that. We also have a speed, 7,000 miles per hour approximately. So we got some kinetic energy. All right, now, and that's at the same time. So from that, we can figure out the total mechanical energy of the space shuttle. And at this point on its orbit. And then what we're going to do is we're going to bring it down from 50 kilometers down at the Kennedy Space Center. Basically is y equals 0, sea level pretty much. And that's going to burn off a lot of energy. So let's kind of put this together. Now, this is a picture of the space shuttle. It tilts itself up a little bit, and it kind of comes in like a belly flop into the atmosphere. And that's so that it can catch a lot of air resistance, and then dissipate that as heat, dissipate all its energy as heat, heating up the air around it and itself. And there's other maneuvers that we could do, that the space shuttle can do. I shouldn't say we, but the space shuttle does to dissipate energy. Now it's about 100 metric tons. Okay. Depending on what they got loaded on board and stuff, and how much fuel is left, and is it fully fueled and has a payload, or is it on the way back so it doesn't have much fuel and it doesn't have a payload, And the landing speed out there at Kennedy has to be about 215 miles an hour. Now, we're going to round that off to 100 meters per second, all right? So 100 meters per second would be about 227 miles per hour. So we'll call it 100 meters per second. That's close enough for government work. All right. And so there, when you land at Kennedy Space Flight Center, y equals 0. So you know the potential energy is there, 0, because you've lost it all. You're down at sea level now. So y equals 0. But you still have a little bit of kinetic. You have a mass, 100 metric tons. That's 100,000 kilograms. And you have some speed, 215 miles per hour, or approximately 100 meters per second. So we can do K equals 1/2 mv squared at the landing strip. And GPE is automatically 0 because it's at sea level. And so we can figure out how much total mechanical energy is left over from orbit. Right? You got to have a little bit. You can't, you don't want to drop like a rock. You want to have enough to, they can, in the atmosphere, they can maneuver the space shuttle. All right? It's not like a fighter plane, but they can maneuver it. Boy, would that be a thrill. Coming in from orbit and landing at Kennedy in the space shuttle. Oh my goodness. What a plane. What a flying machine. All right. So here we go. We're going to do one more thing, and this is realistic as well. I read the article from which I got that image from the Air Force observation, and that was about 12 minutes before touchdown when they got that. So it was somewhere over the Pacific. All right? And they nabbed that photo, because they start their deorbit maneuver like over the Indian Ocean. And then they come in over the South Pacific, and one of the ways they burn off energy is they do these gigantic S-turns in the atmosphere. And so it's incredible. The space shuttle, it'll start an S-turn by Australia. It'll go through one S-turn, and by the time it comes out of its S-turn, it's over Hawaii. And it's thousands of miles. But for those guys, it's just a minute of work, because they're going so fast. So it's fantastic to think about. All right, so 12 minutes at 720 seconds. All right, so we're kind of converting things into seconds, kilograms, and meters. All right, and we're going to do GPEs, and we're going to do kinetic energies, 1/2 mv squareds, and we're going to add them up to the total energy, and we're going to try to analyze it. So here's the question that we want to try to answer. All right, now I'm going real slow. I'm trying to go step by step. And I want you to ask questions as we go. Don't feel shy to ask questions. So how much energy is dissipated? We've got to have at least 100 meters per second worth of kinetic energy at Kennedy. And we got buku total joules up there on orbit when we got that snapshot, 9.1, Mach 9.1. That's really burning a lot of kinetic and potential energy up there. So we're going to try to calculate those numbers and see how much is dissipated and how quickly. So that's the second question. How quickly is that energy dissipated? So we're going to figure out the amount of energy that it loses to the atmosphere, the heat. And then we're going to basically divide that number of joules by 720 seconds. And that'll give us a power rating of how much energy and how quickly is being dissipated. All right? So that's kind of our strategy for the next. Now, let's go to a diagram. And here's the space shuttle, the little teeny picture of it there. It's the same picture, actually, but I just shrank it down. And it's above the blue curve of the Earth, so this is above the Pacific. All right, and that's way, way, way out of scale. The space shuttle itself would be like a little dot. It wouldn't even be a dot. It would be a fraction of a dot in this scale. But let's go with what we've got. Now, 100 metric tons, that's 100,000 kilograms. All right. And its speed up there, 3,130 meters per second. I converted the Mach 9.1 into meters per second. All right, so there's V1. All right, and we know that the elevation is about 50 kilometers or 50,000 meters. So if you think about it, everything that we've got up there is enough to calculate 1/2 mv squared and also mg delta y, because we got a delta y of 50,000 meters. All right. Now, let's do the kinetic energy first, 1/2 mv squared. We've done it several times. And this one's ginormous, but you can still do it. And then we're going to do GPE minus MGY above sea level. And then we're going to add them up to get the total mechanical energy, KE plus GPE. Okay? And when we calculate that number, that's going to be the stuff that has to be dissipated almost to zero. And you have to have a little bit. You can't dissipate all of it. All right? Because you still have to have some, you got to go on the landing strip. But we're going to do the landing strap too, and we'll figure out how much it has to retain in terms of energy. All right? And as I mentioned, there's various braking methods. But basically, you're trading altitude for kinetic energy, and you're trading altitude for a lot of heat energy. And the space shuttle and any reentry platform, like this Dragon capsule that they're almost ready to start using with astronauts, take them up to the space shuttle and stuff. Those things get really hot too. And the space shuttle gets really hot. The space shuttle is got a ceramic skin. It's incredible. Most aircraft are made of metal. And in the early days, they were made of wood and canvas to keep things light. And then they went to light metals like aluminum. But the space shuttle, they got to use this is basically made of bricks. It's incredible. But it still flies, and it still gets the job done. It's an incredible machine. All right, so we got to have a lot of heat energy dissipated. All right, let's get the kinetic energy squared away here. Oops, I went backwards. All right, here we go. Back through this. All right, here we go. KE1, position 1, 1/2 mv squared. So we've got M, that's 100,000 kilograms. And we've got V, that's 3130 meters per second. So all we got to do is do this. All right, so that's 1/2 mv squared. And, these are some big numbers, but it's just the same thing as we've done several times. It's just a big number. All right, so it's 0.5 times 100,000 kilograms. And then 3130, if you square that out, it's 9,796,900. Anybody verify me on that? See if you can. Okay. Anybody over here on the right? Okay. How about you guys up in front? Are you calculating? You got a worried look on your face there in the middle. 3130 squared. You got it? Good. All right. So we got verification left, right, and center. So that's good. All right. Now you multiply those babies together. And now, you know what, guys? You're going to have to start using scientific notation because the numbers are starting to get pretty ginormous. Although we're not going to have to do calculations on the test this way, we are doing it today, and we're doing it step by step. All right? Now, 9,796,900, that's 9.7969 times 10 to the 6. And then 100,000 is 10 to the 5. All right? And so you got a whole lot of powers of 10 here. But in the end, it's going to come out to this. 489.8 times 10 to the 9. And guess what? It's kilogram meters squared per second squared. As usual, that's a joule. That's what we're supposed to get. All right, now, the reason I put 489.8 instead of 4.898 is because I want to use that factor of 10 to the 9. If I did it strictly in scientific notation, it would be 4.898 times 10 to the 11. Raise your hand if you got 4.89 and a little 11 up in the, you did? A couple of you? Okay. All right. Now, so what we're doing is we're moving the decimal point over, and we're going to use 10 to the 9, and so 489. So my wonderful students, how much energy is that? That is 490 billion joules. 10 to the 9 is a billion. So we pretty much got 400, let's round off to 490. And my wonderful students, that is a lot of joules. And that's just the kinetic energy. You know, we got to do the potential energy next. And that's going to add. Right? Now you may say to yourself, how come this has any kinetic energy up there in space? Well, don't forget, when NASA launches that thing, they have to get at a certain elevation, but they can't turn the rockets off when they get up there. They have to get it to an elevation and give it the right orbital speed for that elevation. All right, so they got to put some kinetic energy on it, as well as some GPE to get it up there. You know, so altitude and then some. And this is how much extra at this elevation, anyways. 490 billion joules. It's ginormous. All right, let's do so we got that written down, 490 billion joules. Now let's do the GPE minus mgy. All right, and y is 50,000 meters, 50 kilometers. So here's how that looks. I've got a minus sign. I've got 100,000 kilograms. That's 100 metric tons. So that's a good round number for the space shuttle. Negative 9.8 meters per second squared. And then the altitude above sea level, 50,000 meters. And hey, you guys, that's actually not that bodacious. 50,000, that's 5 times 10 to the 4. 100,000, that's 1 times 10 to the 5. So we're looking at about 10 to the 9 joules here again. And if you calculate it out like this, see, I segregated my powers of 10. Let me turn around and point this out on it. Okay, I've separated, right here is 10 to the 5. And over here, this is 10 to the 5 times 10 to the 4. So I parked my 5 down here. I parked my 1 over here. And then 10 to the 5 and 10 to the 4 multiplied together is 10 to the 9. Now, I didn't do anything with the 9.8, but I did cancel the minus signs. So I've got a positive number, 1 times 9.8 times 5 times 10 to the 9. All right. So anybody verify me on this? 49 times 10 to the 9, or 4.9 times 10 to the 10. Anybody got 4. Okay. Anybody over here? Okay, good. What about you guys on the right? Got it? Okay. So 4.9 times 10 to the 10, or in terms of billions of joules, another 49. All right. So let's park that up here. All right. So 49 billion joules of potential energy. So the total energy, my wonderful students, is approximately 539 billion joules. That's capital E, the total mechanical energy. That's just the sum of 490 plus 49, approximately. We're kind of rounding off a little bit to the nearest billion. Now, I calculated the kinetic energy at the landing strip at 100 meters per second. It's the same way. That's 0.5 billion joules, half a billion joules. All right. And make a note there. You can verify that tonight. when you're studying, getting ready for your homework. Homework 6, I think it is. All right? Homework 7. Oh, the one we just did is homework 6. Okay. So, anyways, you can verify this. Well, here it is right here. Okay, so there's the final kinetic energy at Kennedy. All right, you see, you got to have a little bit, coming in, you got to have a little bit of maneuvering speed. Just line it up right and stuff like that, because you don't want to end up in the drink at the end of the strip. Raise your hand if you've ever flown down to St. Thomas in the Virgin Islands, U.S. Virgin Islands. And if you fly to St. Thomas, you cut the airstrip, the landing strip. It's so long they had to build it out into the ocean, a little bit out on a jetty. And the weird thing is, you come in from the sea, and you take off from that same area, and you come in from the sea, and everything looks good until you get near the end of the landing strip, and then there's this big cliff right at the end of it. And then, so it's kind of exciting going down there. I used to live there, so that's why I know about it. It's a beautiful place. I love going down there. And then when you take off, you go to the seaside end of the strip, and you take off right toward those cliffs. So you better make it and get over those cliffs and up into the air. And they always do. But when I was teaching down there, I was teaching at University of the Virgin Islands, and which is the state land grant college. It's like Florida State of the Virgin Islands. I just had a blast living there. It was a great place to teach. This UCF and UVI are my two favorite places I have two favorite colleges or universities to teach. So this is the amount of energy that you have to have left. Now you haven't got zip zap for potential energy because you're down at sea level. So y is equal to 0. You don't have that. You can't capture any more. But you got to have this much. So you got to. So here's the amount of energy that you've got to dissipate. 539 minus 0.5 billion joules. All right. So there we go. So there's the amount of energy dissipated. All right. Now don't worry about having to calculate some re-entry of the space shuttle on the test. But I might ask multiple choice questions about this, kind of generic questions. So 538.5, if you keep an extra digit there, times 10 to the 9 joules. Okay? And so that's 1 billion joules. Now, you have to dissipate that energy in the 12 minutes it takes to come down from that position. Going over the rest of the Pacific and then over California, Texas, and on down here to Florida. Question? Because it's 1 billion, and I want to work in billions. I mean, I could use any exponent there, but I have a secret reason, a teaching reason to use 10 to the 9, because it's 1 billion. And there's other things that dissipate billions of joules or produce billions of joules per second. Okay, and so that's why I want to do it. All right, so here's my dissipation rate. The change in the total energy divided by the elapsed time. So 720 seconds in the denominator and then 538.5 in the numerator. So that's the amount that we dissipate into the atmosphere, basically, through heat. All right, and we still have to retain half a billion joules for landing the beast. Maneuvering and getting everything lined up and stuff. So if you do that calculation there, verify me on this. 0.748 billion joules per second. Anybody verify me on that? Okay, 538.5 divided by 720. Any verification? You got it? Okay. How about over here on the left? Got it? Anybody on the right? Yeah, okay. All right. Now, as now, what is your name? You were asking me about the 10 of the 9. Eliza. As Eliza was asking me, Dr. B, why are you concentrating on billions? Because this is, you could just as easily write this 748 million, and that's true. But the reason I want to uh, compare it to billions is because this unit of measurement, joules per second, it's an energy dissipation rate. And that's known as power. The amount of energy produced, used, or dissipated per second in joules per second. So 1 joule per second is the same as a watt. All right? And everybody knows that you buy a light bulb, like 40 watts or 12 watts or whatever it happens to be, and little tiny flashlight bulbs are, like maybe 1 watt or not even, like a tenth of a watt. And hair dryers, you're talking maybe 1,000, 1,500 watts, 2,000 watts for a fancy hair dryer. Microwave, same. Maybe 1,000 watts, 1,500 watts for a microwave, depending on how big it is. Right? So this is 0.748 billion watts. Now, what is a billion watts? Well, the scientific prefix for billion is giga. So this is 0.748 gigawatts, or as we say, 0.78 gigawatts. And that leads us to ask this question. What the heck is a gigawatt? All right. Well, a gigawatt is a lot of energy production. And, the spacecraft burns off, at the rate of, 0.748 gigawatts. And that's a lot of energy. But what other things are there in this world that operate at the level of gigawatts or a few gigawatts or half a gigawatt, other than the flux capacitor, which operates at 1.21 gigawatts? But that's in a movie. Well, here's something. Grand Coulee Dam. Just about the biggest dam that we have, hydroelectric-wise, out in Washington State. And I've been down in through the guts of that dam. It's pretty cool. It's 550 feet tall from the highest water level down to the bottom, and all that MGH gets converted into electricity with turbines and stuff. And you live there? Yeah, it's a cool place. I've been through there. I made sure to go through there. Yeah, so Grand Coulee Dam, 6.809 gigawatts when it's all online. That's how much power it produces. All right. So that's about, I don't know, almost 9 times, 10 times as much as the space shuttle dissipates. All right. And that's how much this thing produces. So in terms of gigawatts, what the space shuttle accomplishes is kind of amazing. And it does it in 720 seconds, 12 minutes. It dissipates a whole lot of energy on the order of size of our biggest hydroelectric dam. Now, if you go down here to one of our nuclear plants, which we have 2 or 3 of them here in Florida, I'm sure you can look up the gigawatt rating for the different nuclear plants. But I love Grand Coulee Dam. If you raise your hand if you've ever been out west, like to Colorado or Utah or something like that. Man, I tell you what, the rest of you have no idea how awesome it is out there until you actually go out. I mean, here's one thing. There's no cockroaches. There's no hurricanes. There's no sweaty thunderstorms. It's hot during the day, cool at night in the summer. It's yeah, they got those, but we got those here in Florida too, just not as bad. The skies are clear. I mean, I used to live in Montana. Oh my goodness, yeah, I'm so homesick for Montana, more than I am from where I grew up, New Jersey. I mean, hardly anybody wants to be homesick for New Jersey, but Montana, yeah. And so I highly recommend. And Grand Coulee Dam, it's out there. It's in the it's between the Rocky Mountains and the Cascade Mountains. It's this big plateau. They call it the Inland Empire, and it's they grow fruit out there. They have all kinds of irrigation. It used to be a desert, and it's still desert-y, but along the rivers and different places, they have all these orchards irrigated up. It's just fantastic. And the fishing, and the skiing, forget about it. Oh my goodness. And mountain climbing in the summer, trout fishing or mountain climbing in the summer, trout fishing in the summer, and skiing in the salmon. That's on the west slope. Yeah. Yeah, oh yeah, definitely. They got salmon. This is the Columbia River. So the salmon go up the Columbia River to spawn. They go around the dam. They got a little things fixed up for the salmon. Boy, it's making me homesick for Montana.
I like where this class is
Yeah, I know. Well, let's go up to space. And let me finish by my comparison of these two formulas. All right. Even in a complex situation like the space shuttle docking with the space station, I mean, that's a big, big maneuver. You got to get it right. You're up there in space. You can't have everything bolted down into position, which means you only have to move one thing. You have two things moving at the same time. And so you got to get it right. Anyways, the impulse equation on the left is usually, as I've said before, the best way to start for one of our two classic tasks, calculating the stopping time, delta t. All right, it's not the only way. You can still use F equals ma and 1/2 at squared and all that stuff, the distance triangles and stuff. But usually this one's good. And then the second formula on the right, that's the work formula. F delta x, that's the work. And that's equal to the change in the kinetic energy. And we just calculated a big change in kinetic energy. Matter of fact, you could from this, you could figure out the average aerodynamic drag force on the space shuttle that slows it down. Because you couldn't do what the space shuttle does on the moon. On the moon, there's no atmosphere, so you couldn't land the space shuttle this way by dissipating heat because there's no atmosphere, so no heat dissipation. But you can figure out the average force knowing that we've lost, like almost 490 billion joules of kinetic energy, delta KE, and we know how far down we've come, 50 kilometers, so we can figure out the average force there. That's kind of interesting. But in general, those are the two formulas, and they'll be on exam too. They'll somehow, some way. So don't worry about memorizing them. Remember, we have the formula matching in some form or another. Sometimes they even put a formula into the problem. If I don't have enough space in the matching section, I'll put one in the problem so you can use it. But you want to know how to use it for stopping time and stopping distance, are two classic tasks for this part of the curriculum. All right? Now, let me pause for questions. Pretty good pile of energy dissipated by that space shuttle, huh? Never thought of it that way, did you?
I do have a question.
Yeah, go ahead, Andrew.
It's a couple slides back, but the equation where you've got 438.5 for, I think it was for
The amount dissipated.
Yeah, the amount dissipated. Um, I guess I'm,
No, that's the 438. Yeah, that's the amount dissipated, I guess. Yeah.
so, I guess my question is,
Or 500. What was it? 538 or 438? I think 538 was the total mechanical energy, wasn't it?
so I've got
Yeah.
538.5 is what the
Total
top,
mechanical energy is, yeah.
so where, where did that number, I mean, I've got part of that number because when I came up with it, I came up with 538.8.
Yeah, I rounded off a few places. So,
Okay.
all right. So Andrew was asking me, why do you have 538.5 instead of 538.8, which is what I got? And the reason for that is I was rounding off a little differently than you. So you're it's close enough for government work, as we say. All right, let's keep going into another topic, and that's angular momentum and um, the whole idea of things that spin and turn. And we've already talked about one set of things, orbits. You know, we've talked about geosynchronous orbit, low Earth orbit, LEO. We've talked about high eccentricity orbits for spy satellites, you know. And so um, all those things, the orbital state is defined by physical parameters, radius and mass, and then of course the mass of the Earth, if that's what you're orbiting. But then the description of the orbital state can be um, described in terms of its energy state and something else called angular momentum. Okay, those are the two things. So we don't need the momentum, the regular momentum. We need the spinning momentum or the angular momentum for a gravitational orbit. Right. So we're going to get into those concepts for the next 25 minutes. Let's keep going. Let's do another iClicker question. And this one, so go ahead and turn on your iClicker. And this one's going to be multiple choice, so just turn it on. And we'll do a clicker question together. And let's see. Read this one carefully and answer. Which way does the seesaw spin, at least at the start? Clockwise, counterclockwise, or not at all? And maybe make a diagram of this too. So A, B, or C. And try to add a diagram of this into your notes. Yeah, don't forget to look at those masses. The black dot is 40 kilograms, the white one is 50. So for the first few degrees of motion, if any, does it go clockwise or counterclockwise, or doesn't it go anywhere at all? Okay, 15 seconds to vote. Starting now. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. And yeah, it looks pretty good. Most of you guys are geniuses. It does go clockwise. And so let's take a look at this diagram. This is a diagram from the book. And I have a whole discussion in there about two kids on a seesaw, kind of like this. And here's one of the quotes: "My little daughter can defeat her brother and leave him stranded up in the air if she gets farther out." So this is the weight force of the sun and the excuse me, let me get over to the other. Here's the weight force of the sun. Here's the weight force of the daughter. This is a diagram from the textbook, so please do your reading over the weekend about this stuff, okay? And the concept I want to talk about first is something called torque, Torque. And this is the thing which you get, a colloquial term for torque is leverage, all right? So if you can't, like you can't get leverage on something, you can't move it, maybe get a longer lever or something and really, like a big pry bar, or a landscaping bar and really, like when I'm in the garden and I'm excavating a tree or a shrub or something, you got to use the big landscaping bar for that. So torque and leverage. The amount of torque, which is the rotational analog of force, depends on where your position is. So, like for the seesaw, where are you on the seesaw? Are you two meters and 2 meters each side, or are you different? Is one of them 2 meters and the other one's 1.5 meters? That changes the net amount of twisting torque, and also how many newtons with which you push or pull at that point. All right. So for instance, and a good example of that is a wrench like this. And this is a big one, all right? And I've seen guys with big crescent wrenches like about this long, that are made for really big pipes. And there's even bigger ones than that. And I've even seen a guy, when I remember in grad school, we had this guy that was working in this one lab that had all these pipes where they had pumps and they created vacuums and stuff for certain experiments. And he had one of these big crescent wrenches trying to get some of the pipe fittings, and he actually snapped the pipe wrench, the crescent wrench in half. It was incredible. He couldn't get it. He couldn't get it undone, and he snapped the wrench. I've never seen that anywhere else, but it happens. So let's take a look at an example. Very common example: a door and a hinge. Right. So here's a door. Capital H is the hinge. And if you push on the door with force F1, so in other words, straight up like this and all the way out at the end, then you're going to get maximum leverage or maximum torque. And if you do that, the door will open the fastest. And instinctively, we know that. We don't even think about it. And that's where we put doorknobs. We put doorknobs all the way on the other side, most of the time, unless you're in a fancy mansion or something. But, most doorknobs or even levers, that let you in the door are as far away from the hinge as you can get and still be on the door. All right. So if you push straight in, you'll be able to open the door. Now over here, this second one, where's my thing? Okay, this one over here, F2, force number 2, that guy ain't gonna get anything. That's like pushing straight into the hinge. I mean, he can be Arnold, but if he's pushing straight into the hinge, he's not gonna get jack for torque. All right? So it depends on where you apply the force and the direction in which you apply it. So you can have Arnold on the first one, and he's going to open that door. But if you have Arnold on the second one, I don't care how many muscles he has, he can't open it because he's just pushing it straight into the hinge. There's no give. The door won't spin either way if you push straight in like that. All right. So this one doesn't open. All right. So let's take a look at this idea of pushing at different spots. And here's another diagram. Actually, I think many of these diagrams are from the textbook. So this is a good enrichment on the textbook, on what I've written in the textbook. So what happens when you push at different spots? All right, where you apply the force is pretty important. So let's take a look at this. All right, so let's take a look at this plank. So a 2x4, for instance. All right, and you're floating it on water. All right, so that's what that blob of blue stuff. And this is from page 74 of the textbook, when the textbook used to have pages, which it doesn't anymore. So, but you'll see it when you look in there. All right, so this 2x4 is what we would call an extended object. Now, a baseball, cannonballs and stuff, we think of those as point objects. And they're rigid, they're spherical, and we think of, everything that we've done up to this point, even the space shuttle, we thought of that as a rigid object that, you just think of the MG centered at the center of mass of the space shuttle or any other object that we've studied. But if you do think of a real object like a board floating on water, you can get a lot of complex trajectories. If you're just pushing a baseball, it's going to accelerate in the direction that you push it or that you pull it. But this is different depending on where. If it's extended, you can, a point object, you can only push it at one place, the dot. All right. But for a board or something like this, an extended object, you can push it at different places. So the trajectory that you get depends. First of all, it does depend on F equals ma. All right, you got to push a little bit, but also on where you apply the force, like F1 and F2. Now, F1 is pushing right at the center of the board. So we'll consider that to be the center of mass. Now, if you push the center of mass, the whole board will go in the direction that you push. All right. You'll get some F equals ma. You'll get some acceleration from it. If you push over here, like force number 2 at point A, now that's away from the center of mass, guess what happens? You get a little bit of F equals ma acceleration, and you get some spinning. All right? So the force F2 will also put some spin on it. All right? So it's a more complex motion. All right? So it's going to move across the pond, yes, but it'll spin as it goes. In this case, it'll spin clockwise. All right? Now, the impulse formula, F delta T, was equal to delta P. So force and momentum are connected and conceptually connected through the impulse formula. All right? Now, we have a similar situation with torque, where you put your force. And that's called angular momentum. So this idea of torque, a force affects the momentum, delta P. A torque affects the angular momentum. And that's what we're going to try to figure out right now. All right, so here we go. Angular momentum states. All right, so as I mentioned, the rotational analog of F equals ma is torque. All right, and here's the impulse equation. Well, this is Newton's second law. It's not the impulse. You can see the impulse equation in this, though. F net is equal to delta P over delta T. All right? And so what we want to do is try to get some kind of an analog to that equation, but related to torque. In other words, to the distance away from the center of mass, or the spin axis in this case. If it has an axle, that's a fixed spin axis. The distance away from that you apply your force, and the direction relative to that axle. So if you're looking at this disc and you want to spin it up, you want to try to kind of cut it along the edge, kind of whip it around like that. If you push straight in toward the axle, it's not going to spin. All right. So think about if you watch, what is that show where they spin the thing? Wheel of Fortune. And those guys, they have those little pegs, right, that they grab a hold of and they yank it, but they don't push it towards the center. Otherwise, now who's that guy? Pat Sajak, Alex Trebek. No, he's on Jeopardy. Pat Sajak. I've never actually watched. I've seen like about in my entire life about 5 seconds of the, what is it called? Not Game of Thrones. Uh, the Pat Sajak game. What is that called? Wheel of Fortune. I've seen about 5 seconds because I just click past it as I'm going through for some other channel. But if you tried to push inward on the Wheel of Fortune, Pat Sajak would say, "Come on now, contestant, pull tangentially, or you'll get no." Well, he wouldn't say that, but he'd tell you, "You ain't got to pull it this way." Because if you push radially into the axle, it ain't going anywhere. You don't get any money. You don't get any vowels or any consonants or anything like that. You're toast. All right. So the thing that changes by a torque is called angular momentum. So here's a little vocabulary blurb, and this is actually from an old textbook that I used to use, but it's pretty good. Translational momentum or linear momentum is the momentum an object has, mv, from just moving from point A to point B. That's what we call translational motion or linear motion along a straight line. All right. Rotational motion is if the thing's spinning about its center of mass, or maybe spinning about some axis, or maybe you're using a wrench, so you're spinning it about the head of the wrench, and you're out here at the other end cranking on it. So that's rotational or angular motion. All right. Now a combination motion, things like I mentioned, the 2x4 floating in the pond, it could go in a certain direction and be spinning. All right. So you could throw a 2x4 up in the air and give it a little bit of a kick so that it spins, and it will go end over end. Football, that's the perfect example. End over end. Kicking a field goal, the thing it's spinning, and it's also going towards the goalposts. Now, here's a cool experiment. This is a strobe photo. So give me your eyeballs on this one. This is a strobe photo. It's an actual strobe photo of a crescent wrench, and it's been thrown from the left side to the right side with a little bit of a spin. All right. Now, the natural center of mass of the wrench, the wrench is asymmetric, so it's not right in the center, half the length. It's right up here. You can see these little pluses, and I don't know who made this photo, but they could have made it in like day-glow green or something like that to show, but they used probably black electrical tape or something like that. And I'll put some little diamonds here. Right? So these little blue diamonds, I'm going to put them right over the center of mass. Right? So that's the center of mass. And you can see that this thing's just percolating along. Linear momentum, linear velocity, so many, and it's uniform as it goes. Because the distance between each of those blue diamonds is pretty much the same, but yet the wrench is spinning about that. You checking it out? I saw somebody up here holding up something to see if it's a straight line of stuff. Is it good? Does it check out? Good. All right. So the translational speed is constant, but the spinning, it's definitely spinning. It's got some angular momentum. And this one is on a table that's low friction, I guess. And so it basically, just keeps spinning at a certain rate. And you get about half of a spin on this. What direction is it spinning? Clockwise or counterclockwise? Yeah. If it's moving from left to right, then it's spinning counterclockwise. Now, check this one out. See that? That's a strobe photo of some guy that appears normal, but he tries to entertain people for money by doing backflips on his motorcycle in the air along a parabolic arc, just like that. Now, can you imagine? Can you imagine? And he's going from right to left. That guy. Yeah. Well, can yeah. I bet there's nobody that does it backwards. But can you imagine the amount of times he has to experiment? He can't. Because if you experiment on this and you blow it, you're going to break your neck or something. By the way, did you see that NASCAR racer that walked out of the hospital? I was going to put that in. I'll put it in the slides on Tuesday. It's unbelievable.
I know they do doubles now.
Yeah. I've never been to one of these rallies, but I don't know. I think I'd puke if I watched the guy doing that. All right, it's almost time to dismiss. Let's dismiss here. This is a good place, and we'll talk some more about angular momentum. Homework and reading over the weekend. Check later tomorrow. You're dismissed. I don't know. I couldn't do that. Either of these guys. I mean, that's total insanity.